Have you ever wondered how two things can be made of the exact same parts, connected in the exact same way, but end up being, well, totally different? It sounds like a magic trick, but in the world of chemistry, it happens all the time. Today, we're pulling back the curtain on this incredible molecular shape-shifting.
Right. This is the big question. It's like having one recipe that somehow gives you two completely different cakes. You've got the same formula, the same ingredients, the same instructions, but the results are worlds apart. So what is going on here? How does chemistry make this happen? To figure this out, we're going to treat it like a puzzle, a molecular whodunit, if you will. And our first clue is a molecule that shows off this strange behavior perfectly. So let's meet our molecule of interest, but2-ene. Its formula is C4H. That just means it's made of 4 carbon atoms and 8 hydrogen atoms. Sounds simple, right? Well, here's the twist. Nature can take that exact set of atoms, connect them in the same order, and still create two fundamentally different molecules. Now this isn't magic. It's science. The official name for this phenomenon is geometric isomerism. And the secret isn't what's connected, but how those atoms are arranged in three-dimensional space. The blueprint is the same, but the final construction is different. And that small difference, as we'll see, changes absolutely everything. So, what's the secret? What's the architectural feature that locks these different shapes into place and prevents them from just morphing into each other? It all comes down to one very special, very stubborn part of the molecule. And here it is, the hero of our story, the carbon-carbon double bond. This little guy is the game changer. You see, not all chemical bonds are created equal, and this one introduces a level of stiffness, of rigidity, that is crucial to our puzzle. Okay, think of it like this. A regular single bond is like an axle. The parts on either side can spin around freely, no problem. But a double bond? That's more like gluing two pencils together side by side. Try twisting one without twisting the other. You can't. It's locked. And that rigidity is what forces the other atoms into fixed positions.
All right, so now that we know why we can have these two different locked-in shapes, we need a way to talk about them. We need some labels. And luckily, chemists came up with two really simple terms that get the job done.
And here they are, cis and trans. It's actually from Latin. Cis means on the same side. So in a cis isomer, the important groups of atoms are stuck on the same side of that rigid double bond. And trans? That means across. So in a trans isomer, those groups are on opposite or diagonal sides. It really is that easy to remember. Same side as cis, opposite sides as trans. Okay, so we've got different shapes and different names. But here's the real question, so what? Does this tiny difference in arrangement actually matter in the real world? Oh, absolutely. And you can see the proof in some very basic, measurable properties. Now check this out, because this is where it gets really interesting. The cis version has a higher boiling point, but a lower melting point than the trans version. I mean, think about that. They're made of the exact same atoms, but they freeze and boil at different temperatures, all because of their shape. You can see it really clearly here with the boiling points. It takes noticeably more energy, more heat, to get those cis molecules to break apart from each other and float away as a gas. And why? It all comes back to their shape. So here's the breakdown. Because of its bent U-shape, the cis molecule is a little bit polar. It acts like a tiny magnet. And these little magnets stick to each other more strongly, so you need more heat to pull them apart, giving it a higher boiling point. The trans molecule, on the other hand, is straighter, more symmetrical. It's not as magnetic, but it can pack together really tightly and neatly, like bricks in a wall. This super efficient packing makes the solid structure stronger, which is why it has a higher melting point. And that's really the big takeaway from all of this. In chemistry, a tiny, almost invisible change in a molecule's structure can lead to a huge, dramatic change in how it behaves in the real world. When it comes to molecules, shape is destiny. Which really makes you think, doesn't it? We've just seen how a molecule's hidden geometry has a major impact. It begs the question, what other invisible structures and tiny arrangements are out there, quietly shaping everything around us, from our food to our technology? Something to think about. Thanks for tuning in.